Literally, of all the times that my dad could have walked in, that it would have been totally fine, he had to walk in when I was Googling about. You may be wondering what I was Googling and how I found myself in this situation. Well, for that, we have to go back to the beginning. What's up, y'all? I'm going to start a new series. I don't even know what to call it yet, but basically taking clips from movies and analyzing them with physics to see, could they really happen? Would, like, for example, the main character still be alive, or is that something that is physically realistic to happen? So, if you're new here, I'm Sierra. I'm a trained astrophysicist. So, I went through the traumatic experience of being trained in physics, but we're gonna take that and use it for good here, I guess, or at least for fun. Anyway, if you have ideas on what to call this series, let me know. I don't have any ideas yet. But anyway, today we're gonna start with Tangled. Yes, I realize that this is a cartoon, and it's like a fairy tale cartoon. So I'm already betting that all of the questions I'm gonna ask about it are not gonna pan out as realistic, but you know, we're gonna find out. So let's watch the clip.
Head down.
Head down.
Arms in.
Arms in.
Knees apart.
Knees apart. Knees apart. Why do I need to keep my knees apart?
Okay, we've seen the clip, so let's come up with some questions. The main question I think I want to answer is, would Maximus have survived? And also, would Flynn have survived? So in order to do that, we're gonna take it step by step. We're gonna break it down. We're gonna break it down. Okay, so I think the first thing we want to figure out is the speed which Flynn was going. And in order to do that, we're gonna have to do a bit of Googling and possibly a bit of approximating. So one of the things we have to figure out is this height here of the castle wall. And if we take one of these guys to be approximately like 6 foot, let's say, and in science, I never work in feet, so let's figure out what 6 feet is in meters. Okay. So I think I'm gonna make this line a little better. Okay. Now I'm gonna take this line here, copy it, and I'm gonna paste it a bunch of times so we can try to figure out what the height of the wall is. And just stack them up. So that's 2, 3, 4, 5. Okay. So it's not quite 6, but let's just say, I don't know, approximately 5.5. 5.5 times 1.8 meters is 9.9, so let's just say that it's about 10 meters. Now we have this guy who's gonna jump off the wall and land on the catapult. So if we figure out his final velocity landing here on the catapult, then we can figure out Flynn's initial velocity, because I'm going to assume that all of the speed, all of the energy will just transfer to Flynn from this guy. So we want to figure out what his final velocity will be on the catapult. So pulling up my kinematic equations, it looks like the equation we want to use is this one. And in this case, I'm going to imagine that he stepped off the wall instead of jumped, so I'm going to say his initial velocity was 0. The acceleration is the acceleration due to gravity, and this distance is going to be the height he was up the wall. So, okay, let's see if we can estimate this a bit. I think we should probably do it from right here. So that's going to be 1, 2, 3.5, let's say. Height equals 3.5 times 1.8 meters. 6.3 meters up the wall. The total wall is 10 meters. Yeah, that seems fine. Okay. So now we also want to solve for the final velocity, because that's the thing we want to know. So I'm going to go ahead and get rid of this because it's 0 and just say 2gh, which is 2g 6.3 here. Okay, I got a final velocity of 11 meters per second, which remember is then going to be the initial velocity of Flynn. Well, let's write down what we do know. So we always are going to know the acceleration in the y direction, because that's gravity. We know the initial velocity now, which is 11 meters per second. We just solved for that. We aren't going to know the final velocity. That's the thing we're going to want to solve for. We have the height, which will be the distance in the y direction of the wall. But actually, if you look at this scene, it shows him going above the height of this tower here. So we're going to have to do a bit more estimation. You can kind of see that the tower starts here. And let's imagine it looks something like that. Is it more pointy? I don't know. It's okay. So I'm going to say it's probably, even if it was more pointy like that, it might be another 2, 3 meters in the sky. Let's see. I want to paste that. Yeah, let's say another 1.5 of those lines. So that's going to be 1, 2, 3, 4, 5, 6, 7.5. Okay, so that's like 7.5 times. We said each one of these lines is about 1.8 meters. Nice number, that's 13.5 meters. Not sure about the distance. Oh, I can calculate the time from the video.
Why do I need to keep my knees up?
And the video was initially catapulted at 1 minute 16 seconds. And then he lands at 1 minute 21 seconds. So if we take the absolute value of that, that's going to be 5 seconds long. Okay, I say that's a good amount to start with. Let's see how far we can get with this. One last thing we have to take into account is that this catapult here is at an angle, which means that Flynn is launched at an angle. In order to use the kinematic equations, it's very important that we break down everything into its components. So we need to know what the initial velocity is in the x direction and what it is in the y direction. Because I, watching the video, looked at the trajectory, he's kind of have a really high arc, something like that, which makes me think that even though this angle looks a bit larger, I am going to say that the angle is about 30 degrees, I think. So if we have our triangle here, let's make that flat. And Flynn is up here being launched, and this angle here, whoops, is going to be 30 degrees actually. So now we're going to have to do a bit of geometry here to get all of our our angles and things correct. So I'm going to take this bottom part and move it up here. And we know that we're going to have some like initial velocity here. So this will be our initial velocity. And we have to break that down into the initial x component and the initial y component. So if we know this angle here is 30 degrees, we have our z here, which tells me that this angle is also 30 degrees, and that this is a 90-degree angle, so that means 90 minus 30 means that angle there is 60 degrees. So I don't know if you ever learned this in school, but whenever I have to do a trig, I always write down SOHCAHTOA to help me out. So if our angle is here, and we need to know our velocity in the y direction, that's going to be on the opposite side of the triangle. And we know our initial velocity, which is our hypotenuse. So we have opposite hypotenuse, that tells us we're going to use sine. So this is going to be the initial velocity times sine of that angle. On the x initial velocity, that length is going to be adjacent to the angle. So that tells us we have the hypotenuse, the adjacent part, and that tells us we're going to use cosine. So let me calculate that out. 5.5 meters per second. And in the y direction, that's going to be about 9.5 meters per second. Okay, so just a quick mental check. Our y direction velocity is higher than the x velocity. So I think that's good because we saw the arc going quite high up. Alright, so we want to find our final velocity, which is going to be the components of the final velocity in the x direction squared plus the component in the y direction squared. And that'll give us our full final velocity. The velocity in the x direction actually isn't going to change. We've started out what we have initially, and we're going to assume there's no type of drag. There's nothing else going to be accelerating it, so we're going to assume that it remains constant. So actually we can go ahead and plug that in. What did we say it was? 5.5 squared plus, and then we still don't know what this is yet, so we can solve for that. Okay, so I think the best equation to use is going to be using the initial velocity minus gravity times time. And we have our initial velocity at 9.5 meters per second. Then we have 9.8 meters per second squared, and then we said our time is 5 seconds. Okay, so now we have minus 39.5 meters per second. That minus just tells me it's going in the down direction because I have arbitrarily chosen up as my positive direction. Okay, so now finding the full final velocity, we have the x direction, and now we have our y direction. 39.9 meters per second. That's really fast. No chance this horse survives. Next, we want to find the force due to impact. So that's going to be the mass times the acceleration. In this case, it's going to be the deceleration, how quickly it stops, or how quickly Flynn stops. So we'll have to estimate his mass here. Does Google know? Oh, cool. Google is saying his mass is 165 pounds. That is not mass yet, though. This is weight, so we're gonna have to convert it. Is approximately 75 kilograms. Okay, so that's gonna be our mass, 75 kilograms. And then we want to know how long it takes, or the deceleration. So this is going to be the final velocity you end up with is 0. So he's become stationary on Maximus's back, and then minus the velocity that you start with, so that's 39.9 meters per second here. And then we have to figure out the time it takes for him to go to 0. Okay, let me watch it again. He stops real fast. He just fully stops, bro. I don't know, let's be generous. Let's say 0.5 seconds. 5,985 newtons. That's a lot of force. Okay, how am I gonna figure this out? No way. I really couldn't find any information about this on the internet. So I asked ChatGPT, and I put in the weight of Maximus, which Disney said is 1,000 pounds. And ChatGPT estimated the braking force at 9,810. So Maximus braking force is estimated to be at 9,810 newtons. Oh, wait, so Flynn could have done this and not killed Maximus? Huh? What? How does that make sense? I fully thought that this was gonna be a dead horse. I guess horses can take a lot more. Either that or the internet just really doesn't know. Which is probably good. I mean, maybe that shouldn't really be a tested thing. What's the maximum force a human can take before dying? Interesting. On a physics forum, it says that the amount of force required to kill a person, of course, varies greatly depending on a lot of factors, but research suggests that a force of 3,500 newtons or more could be fatal for most adults. So the thing about this here is that we calculated the force that Maximus feels when Flynn lands on him. However, that's the exact same force that Flynn feels as he's landing on Maximus, which means this 5,000, almost 6,000 newtons of force that he's feeling is most likely going to kill him, or at least really mess up the crown jewels, if you know what I'm saying. No, I'm gonna call that a no. So humans can take less than, 3,500 newtons. So that is a no. We're gonna say Flynn died. Sheesh. Okay, but what if he didn't die? Bro is gone. I went through the physics and I calculated the force which he lands on the horse. I was just curious. Well, it's so much force that actually he would probably die. But let's say if he didn't, I was just like,
I think he would be impotent for the rest of his life.
Yeah. So anyway, that's what I've been doing. That was not embarrassing at all. Literally, of all the times, my dad just walked in when I had all the information about how much force it takes to break up. You know. Anyway. That was an interesting conversation. With that trauma aside, he did reference that I have this thing on my desk that everything is figure outable. Is that a good name for the series? That's all we have for today. I hope you enjoyed, and if there are other video clips you want me to analyze, or even if you still have names that are better than this, let me know, and we'll keep the series going. Thanks for watching, and I hope you found this physics very fun and entertaining.